Hi, so in this video we are going to try to put everything together in this special playlist. So what we are going to do is, for the biasing, since there's a whole video on biasing on the other playlist, I'll try to be as brief as possible. Then we move to other things that will look at summarizing everything together. So in biasing we have four techniques. Now, instead of having our VBE here with our microphone signal, we want to find ways of creating the biasing voltage from the same VCC. So method 1, we looked at a simple biasing where we placed a biasing resistor on the VCC then we needed to put a capacitor here to prevent the current drawn from the biasing resistor from going back to the source or the microphone. Rather, we wanted the current to move into the base, and the collector current would be given by beta times the IB. So assuming you had a particular value of IB in mind, then you choose your base resistor that will satisfy this equation: VCC divided by your bias or base resistor should give you the collector current that you desire divided by beta. So, and the issue with this method is the sensitivity to beta, because beta changes whilst the device temperature is changing. So we wouldn't want that. If we want something more stable, then we looked at the second method, number 2, which is the voltage divider. So once again, the coupling capacitor, then you use voltage divider. So it was explained how to select resistor R1, R2. You can refer to the other video where this is taken into details. Then the voltage divider with the emitter RE, which helps to improve stability, and we played with RE in LT Spice in the last video. You can check that one also out. And finally, the with the self biasing, and the advantage here is that, sorry, so it goes like this. And the advantage here is that this point potential is always more than the potential of the base, so it means it's always forward bias, and it uses less resistors or components, so makes it very ideal for integrated circuits where the size really matters. The higher the size, the higher the cost. Okay, so we quickly look at the common emitter stage. So what we mean by common emitter stage is that for the common emitter stage, we give the input signal to the base. So the input goes to the base and the output is sensed from the collector. So this is something that we have used all along. Aside the common emitter stage, there is another stage called the common base stage, where, so we know the gain here is minus GMRC. Then we have the common base stage, where the input is rather given to the base. So maybe I will do another video with LT Spice illustration. Okay, and the output is taken here. All right, so in this, the advantage here, or what you notice here, the difference between the common emitter stage and the common base stage is that, supposing there is a base current VB and the input is given at the emitter. So if the microphone signal is given to the emitter, then what happens to my VBE when the emitter voltage rises? So I have my VBE here. Let's say 700 MV, and the emitter is grounded at 0 when there's no signal. Now as soon as I tie my microphone to the emitter, when the microphone signal goes up by 10 millivolts, it means the emitter voltage goes up by 10 millivolts, and that means that the VBE will now go down to 690 because the emitter has raised from 0 to 10 millivolts. And when the VBE goes up, it means that the collector current IC also goes up, and that means that the voltage drop here will go up. ICRC goes up, and if ICRC goes up, okay, so what I'm saying, VBE goes up when the microphone signal goes down. So assuming the microphone signal goes down to minus 10 volts, then the VBE will also increase to 710 millivolts. Doesn't change anything. The same thing, does that in the earlier statement I said when the microphone signal goes up, which is true. When the microphone signal goes up, the VBE reduces. When the microphone signal goes down, the VBE increases. So here I'm looking at a condition where the microphone signal has gone down, so the VBE has increased, IC will increase, the drop will increase, but the V out will reduce because V out is equal to VCC minus ICRC. So all we wanted to prove here is that the output will also reduce. So in this case, if the input goes like this, the output after amplification has no 180 degrees phase shift. So the gain of this circuit is just like that of the common emitter stage, just that here there is no negative. Okay, then finally we have the common collector, also known as the emitter follower. So for the emitter follower, the input okay, so here the output is taken from the emitter and the input is given to the base. So what happens is, if there's a raise in signal, then the VBE would have to share that change in signal with the VRE, because the loop is completed from the ground to the VBE to the base signal, sorry. So I have the base signal being equal to the VBE plus the VRE. So any changes that occur at the base signal will be shared between the VBE and the VRE. So it can be proven from the small signal analysis that this signal here, the gain is always less than 1, and the formula for the gain is given as this: RE, that's the value of the emitter resistor here, over 1 over GM plus RE. So if RE is far greater than 1 over GM, then we have the gain being almost close to unity. So you might be wondering, how could this be useful? Okay, and it's good to wonder that, because it will feel like, why would I want to use something that tends to attenuate the signal? So that will be answered when you understand the input and output characteristics of these stages, and how input and output impedances are important for a device used as an amplifier, especially, or even as a current source, especially with the output. So the next video we'll look at the input and the output impedances seen from the base, the emitter, and the collector. Bye bye.